So we have already studied about the perfect and imperfect crystal, and normally there will not exist any perfect crystal, because a perfect crystal will be existing only at absolute zero. At all real temperatures, the crystals are imperfect, and the crystals are imperfect because the presence of the defects up to a certain concentration leads to a reduction of free energy. When we consider the effect of free energy of a perfect crystal creating a single defect, especially a cation side defect, which requires a certain amount of energy, and that can be denoted as delta H. Creation of this single defect will cause a considerable increase in entropy. Delta, as we know, entropy, that increase in entropy can be denoted as delta S of the crystal. Thus, various entropy changes may present due to the overall disturbance in the crystal structure. As a result of this considerable increase in entropy, the enthalpy required to form the defect initially is somewhat more. Overall, the free energy will decrease due to this defect formation. That means the entropy of a crystal will increase and the free energy will decrease. And here we have to consider about the thermodynamics of Schottky and Frenkel defect formation. We have to apply the law of mass action to this Schottky and Frenkel equilibria, and the concentration of the defects can be expressed as the exponential function of temperature. The Schottky equilibria in a crystal of NaCl is given by Na plus Cl minus plus VSNa plus VSCl minus, giving Vna plus Vcl plus Na plus S plus Cl minus S. That is equation number 1, where Vna and Vcl are the cation and anion vacancies. VSNa and VSCl are the vacant cation and anion surface sites. Na plus and Cl minus are the normally occupied cation and anion sites. Na plus S and Cl minus S are the occupied cation and anion surface sites. The equilibrium constant for the formation of Schottky defects is given by K equal to Vna into Vcl into Na plus S into Cl minus S by Na plus into Cl minus into VNaS into VClS. All are represented by their concentration. That is equation number 2. The number of surface sites is always a constant in a crystal of constant total surface area. Hence, the number of Na plus and Cl minus ions that occupy the surface sites is always constant. In the formation of Schottky defect, as we know, the Na plus ion and the Cl minus ion will move out of the crystal to occupy the surface site. But at the same time, an equal number of fresh surface sites are created. In fact, the total surface area of a crystal had to increase slightly as the Schottky defects are created. But this effect can be ignored. That is, as per the description, we can write as equilibrium concentration of Na plus S equal to concentration of VSNa and Cl minus S concentration is equal to concentration of VSCl. Thus, equation 2 can be written as K equal to concentration of VNA into concentration of VCl by concentration of Na plus into concentration of Cl minus. That is equation number 3. Now we have to consider capital N as the total number of sites of each kind and NV be the number of vacancies of each kind and hence the number of Schottky defects. The number of occupied sites of each kind equal to N minus NV, and substituting this to equation 3 we'll get K equal to NV the whole square by N minus NV the whole square. That is equation number 4. For small concentration of defects, we can write N as N minus NV. Therefore, K equal to NV square by N square, or we can rewritten as NV equal to N into root of K. That is equation number 5. The equilibrium constant K can be expressed as an exponential function of temperature. That is, K is proportional to e raised to minus delta G by RT. K proportional to e raised to minus delta H by RT into e raised to delta S by RT, because delta G equal to delta H plus T delta S. K equal to a constant into e raised to minus delta H by RT. That is equation number 6. Now, substituting K in equation number 5, we'll get NV equal to N into a constant into e raised to minus delta H by 2RT. That is equation number 7, where delta G, delta H and delta S are the free energy, enthalpy and entropy formation of 1 mole of a defect. For the concentration of vacancies in a monoatomic crystal or metal, the equation 5 becomes NV equal to N into K, and the equation 7 becomes NV equal to N into constant into e raised to minus delta H by RT. That is the thermodynamics of a Schottky defect. Now we can consider the thermodynamics of Frenkel defect. The Frenkel equilibria in a crystal of AgCl can be represented as Ag plus plus Vi equilibria, Agi plus plus Vag. That is equation number 10, where Vi is the empty interstitial site and Agi plus is the occupied interstitial site. The equilibrium constant can be written as K equal to concentration of Agi plus into concentration of Vag by concentration of Ag plus into concentration of Vi. That is equation number 11. Now, let N be the number of lattice sites that would be occupied in a perfect crystal and Ni be the number of occupied interstitial sites. Therefore, concentration of Vag will be exactly equal to concentration of Ag plus I, which is equal to Ni. That is equation number 12. And a concentration of Ag plus equal to N minus Ni. That is equation number 13. For most regular crystal structures, concentration of Vi equal to alpha N. That is equation number 14. That is, the number of available interstitial sites is simply related to the number of occupied lattice sites. That means, in the case of AgCl, alpha can be given a value of 2 because there are 2 thermodynamic interstitial sites for every octahedral site which is occupied by Ag+. Substituting 12, 13 and 14 in equation 11 will get us k equal to ni square by n minus ni into alpha n, or k equal to ni square by alpha n square, because as we have already written as ni square equal to k alpha n square, ni equal to n into root of alpha k. Using the Arrhenius expression, the temperature dependence of the number of Frenkel defects is given by concentration of VAG equal to concentration of AGI equal to Ni equal to n into root of alpha. The Boltzmann constant can be replaced by e raised to minus delta G by RT, or we can write as constant into n into e raised to minus delta H by 2RT. Therefore, from the two equations, that is the thermodynamics of Schottky defect as well as the thermodynamics of Frenkel defect, we have seen that for the formation of both Schottky and Frenkel defects, a factor of 2 appears in the exponential part of the expression for the number of defects. This is because in both cases there are 2 defective sides per defect. That is, in the case of a Schottky defect, one is the cation vacancy and another is the anion vacancy. That is the 2 vacancies per Schottky defect. And in the case of Frenkel defect, there will be a 1 vacancy defect as well as 1 interstitial defect. That means there also 2 defects occur in the case of Frenkel defect. That is, the overall delta H for defect formation can be regarded as the sum of 2 component enthalpies. So this is the very important question that is asking almost in all university examinations, both in the 5-mark question part and also in the essay type. So you have to write the derivations and by heart it. It is a very important part in the thermodynamics of Schottky and Frenkel defects. Thank you.